Okay, here we are back for part 2 of our muscle lecture video here. So we're going to continue with the chapter. If you're following along in the notes, we are at Roman numeral 6, types of contraction. So it turns out that when we contract a skeletal muscle, what you think of is something called an isotonic contraction. This is what you think of. So we're going to start to introduce some terms here, and maybe some of you are familiar with this. When you think of a contraction, what you're thinking of usually is something called concentric. In a concentric contraction, the muscle gets shorter. This is what you think of. Bicep curl, the biceps brachii get shorter. Leg curl, the hamstrings get shorter. Triceps kick up, the triceps brachii get shorter. But there's also another type of contraction under the isotonic category called eccentric. And this is a type of contraction where the muscle is actually lengthening. And I think this will make sense to you once I give you some information about it. You might laugh, but the easiest example I think of is after a really tough leg workout. The day after a really tough leg workout, or for me, after a really long bike ride or long run, when you try and I'm sorry, but it's just true. When you try and sit down to use the toilet, right? Isn't it really hard to sit down in a controlled way because your quads are so sore? I've had to use like the little handicap rail to help lower myself down in a controlled way. Well, that is an example of your quadriceps contracting in an eccentric way. It's when a muscle is contracting as a slowing or brake force. So in other words, if I'm going to sit down in a chair or sit down on the toilet, there are other muscles that are contracting to actually lower me, right? But I have to have my quads contracting to control the force. You could also think about running or walking downhill, or even walking down the stairs. When you're walking down the stairs, your quadriceps, sometimes you'll feel them like they're working. Because even though they're technically lengthening, they're contracting to slow your foot as it lowers to the next step. Hopefully, some of these examples make sense. Interestingly enough, this is the type of contraction that can produce the greatest amount of force. Just the way that the muscle is structured, this can produce the greatest amount of force. Because of this, we oftentimes in rehabilitation settings will focus on eccentric strengthening exercises because they're really valuable for strengthening muscles, but you have to be careful because they can produce so much force. You have to not overdo it. Just took a drink there. Sorry for the pause. Another thing to know about eccentric contractions would be this is going to give you the greatest delayed onset muscle soreness. If you're any kind of runner, you know that running down a hill is actually harder on your legs than running up it. So a common mistake with runners is they just blaze down the hill because they're so excited it's downhill, not realizing that their quadriceps are actually contracting with more force in a lot of ways to slow you down that hill. And you can really shred up your muscles, right? Okay, so those are two examples of a more regular contraction, isotonic. In a concentric contraction, the muscle is shortening. In an eccentric contraction, the muscle is lengthening. And it's lengthening in a way to control a movement or slow a movement. Okay. It's also possible to have an isometric contraction. And this is an example would be like pushing against a wall. There is muscle being contracted, but there is no movement. You can push against a wall. You can push against a wall quite hard, but you may not have any motion. So isometrics, again, are useful in rehab, where we can start, like after ACL reconstructive surgery, we can start to do some isometric quad sets where you just contract the quad and relax. You're not moving the knee at all. You're just trying to get the muscle moving. So you are contracting a muscle, but there's no change in length. The last type here requires a piece of machinery or equipment, and that is an isokinetic contraction. I'm going to skip to the next slide. This is what an isokinetic testing machine looks like. A common brand for these is Cybex. I don't know if you've ever been around one. I've certainly used one. So isokinetic contraction means that we can set the resistance and we can set the type of contraction and speed. So you can set I'll make this easier. You can set, let's just make this easier. You can set the resistance, speed, and type of contraction. I was saying contraction as I wrote that, and I meant to be writing a T. A type of machinery where you can actually purposely program in the resistance, the speed, and the type of contraction you want to do. This can be really cool for strengthening muscles. It's really good as a tool for testing muscle strength. So particularly as an athlete's coming back from ACL surgery, as they're getting closer to being 100%, they'll do an isokinetic test to see the strength in their leg, to see how much strength they've gotten back in their quads and hamstrings. I have some examples here, and I'm not going to ask you to do any type of analysis, but this has some key words on it. So I can look up top and I can see that we were looking at con. And what that means is we were doing a concentric contraction one way and a concentric contraction the other. So this was of the knee. So we were doing one test in one direction where it was concentrically flexing the knee. That's doing a leg curl. And then we were concentrically extending. That's using your quads. It's going to show the speed 60 degrees per second. So you can set the type and the speed. So for example, that was a con, which means concentric, and it was at 60 degrees per second. So what this does is you have one little brace here and one brace here, and the machine will start to kind of move for you. In a concentric, he would concentrically do a leg curl. That's a regular leg curl. But then the resistance would change and he would do a regular leg extension. So the machine has the ability to change resistance. Or let's say he was doing what I like to see is a concentric one way and then eccentric the other. And maybe we do it at 120 degrees per second. So that's fast. In that way, the concentric may be doing like a regular leg curl. But then when the machine is down in this position, now the resistance comes in and it's eccentric. So the machine is trying to push down and he has to try and resist that by contracting his quads on the way up. Same thing as an eccentric contraction. You don't have to know the specifics, only that it's a machine that you can purposely set the speed and the resistance and the type of contraction. Really good for rehab, and it can also be really good for strengthening. So here are some examples. In addition to doing the analysis, we can actually get results. We can test how much effort they put out in joules. Or we can measure torque. You can measure the amount here of the quads and the hamstrings, doing concentric or eccentric. Look, what do you notice? In both examples, which values are higher? If I compare the total work in the quads concentrically to the total work in the quads eccentrically, which can produce more force? Eccentric. If I compare total work hamstrings concentric, total work hamstrings eccentric, which can do more? Eccentric. Didn't we say eccentric is capable of producing more force? And also more torque. So you can actually measure this. Pretty cool. Something else that you can do is you can measure the hamstring to quad ratio. Let's talk about that. So we can gather strength data on the contraction of the hamstrings and the quads. And we can compare. So let me ask you, which muscle group do you think is stronger, the hamstrings or the quads? My little cat is in front of me, Mr. Big. He's looking at me like he doesn't care, as cats do. Well, actually, the quads are stronger. So I'd like you to know that. The quads are stronger. Think about it. We have 4 quad muscles and 3 hamstrings. That's one reason why. We have an additional quad muscle, makes it stronger. Also, it just so happens that more of our everyday activities involve use of our quads than hamstrings, so they've evolved to be stronger. But I had mentioned that we can use this data to see how well someone has recovered after surgery. In particular, they're going to look at this because you want to see the correct ratio, right? The hamstrings should be, so let's write this down. The hamstrings, and you should know this, the hamstrings should be 60 to 80% of quads. Another way of saying that is that hamstrings, or actually quads, should be 20 to 40% stronger. So you can memorize it either way, but that's what we would expect to see. Actually, for athletes, we expect it to be a little bit higher. So for athletes, we'd like it to be 75 to 80 instead of the 60 for athletes. All right, pretty cool. All right, so we're getting here towards the end, kind of. And here we are at Roman numeral number 7, factors that influence force of contraction. We've already discussed some of these. Didn't I already talk about some of the forces at play? If you recall, there was the torque that was produced from the elbow joint. There was the weight of the forearm. There was the weight of the object in the hand. There's also gravity. So remember, there's a lot of things that can influence the force needed to overcome. Looking at all these forces, we had 1, 2, gravity, 3, 4. So we have 4 different forces here that the biceps has to overcome in order to successfully lift up the forearm. I'm not going to ask you specifics here, but I would like you to be able to list some of the forces that a muscle may have to overcome. So we can make a little list here. Sometimes the muscle has to overcome the pull of gravity. A lot of times, muscles have to overcome the force of weight of a bone or a body segment or an object it's holding. There can also be forces from the joint, a torque force from the joint. We can also, here I'll put torque from the joint. As you can see in your notes, It can also depend on, so these are the types of things that will alter the amount of force needed. Other things that play a role, so here we go. Things muscle has to overcome. Okay. Other considerations, as you can see there, type of lever system. Type of lever. We know that the type 3 doesn't give us as much of a mechanical advantage, but we get more control. A type 2 lever gives us more of a mechanical advantage, so it may not take as much force. Type of contraction. Which type of contraction is able to produce the most force? Eccentric. So if I'm performing a concentric contraction, it's going to take a little bit more force. Length of muscle. In other words, where are we in the range of motion? Because remember, it's easiest to produce the most force at mid-range. So if my muscle is already really long or really short, I'm not going to be able to produce as much force. Size of muscle or cross-section of muscle. If I have a larger muscle, it's going to be easier for me to produce more force. So there's so many things that go into it, right? At the very bottom there of that list, we see force-velocity relationship. Okay, there's this picture, and then there's this one. This is what most textbooks will show of the force-velocity relationship. I actually find this to be pretty confusing. So instead of using this one, we're going to use this one. You can see I've hand-drawn it because I think it's easier, right? All right, so what do we want to look at here? Well, along the along the x-axis, we have force production. We're looking at the force-velocity relationship. So this is force production. On the y-axis would be velocity of contraction. Okay? Force a muscle can produce as it relates to the velocity of contraction. Okay, let's understand some things here. We have eccentric down here. So anything below this line is eccentric. Anything above this line refers to a concentric contraction. Okay, so we're going to start with the basics. The first thing we want to understand about the force-velocity relationship is that they are inversely related. Inversely related. Any time that we produce more force, it's going to be at a lower velocity. Anytime that we are producing more force, it's going to be at a lower velocity. Anytime that we want to get more velocity, it comes at the price of lowering our ability to produce force. Okay, so they are inversely related. Force and velocity, when it comes to a muscle, are inversely related. Let's start with the concentric. Okay, so I'm going to point out a certain part of the graph. Let's look right here. So in a concentric contraction, here we have the highest amount of speed, right? The velocity is along this axis. So at this particular data point, we have very high speed. It's high on the y-axis, which is speed. This could be like, 2 meters per second, 4 meters per second, 6 meters per second, 8 meters per second. So at this particular point, I can generate more speed in a concentric contraction. But Where is it on the x-axis? On the x-axis, we're very low, right? So at this particular point, when speed of contraction is high, it's at a low force production. Maybe this is like 10 pounds of force, 20 pounds of force, 30 pounds of force, 40, 50, right? So when we're high with speed, we're low at force. Okay, let's point to a different spot on the concentric. Now let's look down here on the concentric side of things. Now I'm producing more force, but the speed is lower. So this top part of the graph for a regular old concentric contraction is simply showing the inverse relationship. When one is high, the other is low. Okay, how do we use this in sports? Let's think about a bat choice in baseball. If you are at bat against a pitcher who pitches really fast, if that pitcher is pitching really fast, in other words, they're pitching really high in velocity here. Do you want to choose a heavy bat? Of course not. So at a higher, if I need to be able to swing the bat faster to meet that pitch, I need a lower weight bat. That's an example of this force-velocity relationship. In other words, I can't swing a heavy bat and also generate great speeds. Or if I'm playing slow-pitch softball, well, the speed of the ball is very slow, so I can afford to have a heavier bat and therefore generate more force. Let's look at the eccentric. So now, in a lot of ways, we're in the negative direction. And the only reason why this is considered negative, quote unquote, and the only reason why it's in dotted lines is because an eccentric contraction is when the muscle is lengthening. That's the only reason why it's shown as a dotted line and shown as negative. Simply because the muscle is lengthening as it's being contracted. So what do you notice? The concentric curve is more like a C shape, and the eccentric curve is more like a this shape. So their shapes are different, which tells us a little something about this. I have my notes here, hold on. So here, let's pick a spot. This is going to be at a very, hold on, let me look at my notes here. This is the lowest velocity. And I can not produce as much force. So the general relationship is the same. So whether it's concentric or eccentric, the general relationship is the same. When one is high, the other is low. The difference in shape, the fact that concentric kind of has this concave shape, and then eccentric has this convex, what that is showing us is that eccentric contractions can maintain force for longer. Even though it's ultimately the same relationship, compared to each other, even though ultimately the force production goes down at higher velocities, compared to each other, the eccentric is able to hold on to a little bit more force. Same relationship, ultimately, when we increase the speed, the force goes down. But eccentric is able to hold on to a little bit more force for longer. That's what the difference in shape tells us. So this is the example I was trying to give you, and I'm trying to educate you here with Nolan Ryan. You know, his first season in the majors was 1969, when the amazing Mets beat my Baltimore Orioles, but such is the case. Okay. So for a faster pitcher, you would want to use a lower weight bat because you can generate less force against a higher velocity. Okay. That's my last slide, huh? Okay. So you can see we have a couple more things here in the notes, and that's fine. I'm going to add a picture here because I want to show you this. So two more things here. Letter H there, the stretch shortening cycle. A good example of a stretch shortening cycle is, let me use a different color you can see better. Evidence of the stretch shortening cycle is, for lack of a better term, bending down before jumping leads to a greater jump height. Excuse me. Excuse me. If I ask you to do a vertical jump, in other words, if I ask you to, jump up as high as you can, if I just tell you to do it from standing, maybe you can jump 20 inches. But if I say you can bend down first and then spring up, you can jump higher. This is evidence of the stretch shortening cycle. When you bend down, I really cannot draw for crap. I was going to try and draw a person bending down, right? When a person bends down, that's my example of bending. In other words, you flex your knees and you kind of crouch to the ground. When you crouch to the ground, this is a type of eccentric contraction of your calf musculature, your gastrocnemius and soleus. When you bend down, you're actually stretching your gastroc, but because you're trying to bend down in a controlled way, the gastroc is contracting a little bit in an eccentric way to control that movement. It's like a rubber band. You're loading your Achilles tendon, which is attached to your gastrocnemius. When you bend down and you're stretching that muscle, not only is it contracting eccentrically, but it's like loading a rubber band by pulling it apart. The key after this is to have a pause. So to get the best out of this, crouch down in a slow manner, pause for just a second, and then jump up. Stretch shortening cycle. We stretched the gastrocnemius and we loaded it with potential energy. And when we bent down, the gastrocnemius was stretching and eccentrically contracting. Then we pause. And then we shorten that muscle. We contract. Now we do a concentric contraction. You jump. So you first eccentrically contracted it, paused, and then exploded up to concentrically contract it. You first stretched it, and then you shortened the gastroc. The stretch shortening. This is the exact mechanism behind plyometrics. To do a plyometric correctly, like a box jump, you crouch down, pause, and then explode. By doing this, by loading the muscle first with potential energy in the tendon, it acts like a rubber band that you pull back, pause, and then when you release it, it can go farther. By stretching it first, it will be able to contract greater. So many applications for this. Okay, at the very end here, we have injuries to muscles. Just remember, a sprain was an injury to a ligament. A strain is an injury to a muscle. Contusion is just a fancy word for a bruise. Cramping is an interesting topic. There can be cramping in muscle. The exact cause kind of remains unknown. We used to think that it was just electrolytes, potassium and sodium, or maybe lack of fuel, lack of energy, lack of glucose. For a while there, we were thinking that it has more to do with the nerve ending. So I think we have a lot to learn still, but it can be very debilitating. And then the last thing there is delayed onset muscle soreness. After a heavy workout, when you break down the muscles, they will be sore as they're being built back. One thing I want to point out is usually delayed onset muscle soreness is worst 72 hours after the event. So a lot of times after a heavy exercise session, you're not going to reach your greatest fatigue in terms of muscle soreness for 2 days, sometimes 3. That just means we need to give our bodies proper rest and recovery. That doesn't mean they have to sit on the couch for 2 to 3 days after. It can be an active recovery, like walking or getting on a bike and spinning. But I would like you to know that. All right, folks, we're all done. Another chapter in the books. Let me know if you have any questions.